Hi everybody, here's an extension to the heatsink example we did in class earlier this past week. Here's the problem statement here. So we have our heatsink and we put it on top of a computer chip, and we saw that the presence of that heatsink lowered the temperature of that chip. But then suppose there's an alternative heatsink with the same mass as the original, but now you have straight rectangular fins and the same base thickness of these triangular fins as in the in-class example. So somebody comes to you and proposes this alternative heatsink, and so would it work? Would it work better? Would it reduce the chip temperature? So to begin, let's go back to what we had done in class, and here we had straight rectangular fins, and they look like rectangles from the side. Again, we have the chip giving off heat. That heat first goes over a contact resistance to get into the heatsink. There's some small amount of resistance by conduction in the base of the heatsink. And then the fin array itself, which is the area of interest for us, again, it has to be analyzed. Everything starts off at T sub b and it works its way out to T infinity, either through the gaps between the fins or along the fins convecting out to T infinity. So we have copper is our heatsink, so it's a K of 400. We know H is 250. We have the dimensions, the width and the depth are 2 centimeters. The fins have a thickness at the base of 1 millimeter. We're going to use that here in a minute. And the length of the fins are 2 centimeters. So let's go ahead and start by sketching out both of what these heatsinks would look like. The one in class before looked something like this. Again, and there were 12 of these fins instead of the 3 that I'm drawing here, but just for simplicity's sake, we'll go with it. And the new one are now triangular, so they look something like this. Okay, and the idea is that each of these have the same base temperature. We're always starting at T sub b. We're working our way out to T infinity in both cases here. Okay, and the idea is that since the mass is the same as both of the heat sinks, then therefore the volume must be the same because they're both made out of copper. So here we go. So the idea is that if you look from the side, for our heatsink original one, we have an L sub F and a T for each of these fins. Here we have the same base thickness T, but now we have a new length L sub T. I'll call it L sub T for triangular. We know that a triangle is 1/2 times base times height, and a rectangle is just base times height. So it's pretty simple to see that if the volume's got to be the same, then the area of the triangle and the area of the rectangle must be the same. So LF times T is equal to 1/2 times LT times T. So therefore LT must be 2LF. LF is 2 centimeters, so it'll be now 4 centimeters. By the way, from the other problem statement, we know that T is 1 millimeter. We know that H is going to be 250 watts per square meter Kelvin. And we know that K is copper, 400 watts per meter Kelvin. Right. So there's a couple of different ways of then analyzing the triangular heatsink, the triangular fin array rather. So I went back and I put in the charts here, and I think this is what we'll go with for our analysis now. But there's also a table 3.5, and this is what we had done in class. And here we have the triangular. Now they have these two functions here which you probably have not seen. They're called Bessel functions. So we could also find M. So again, it's triangular. So if A, so again, we're going to use A square root of 2h over kt. We have our Bessel functions here. So these are, there's ways of calculating them using MATLAB. There's the Bessel I command. If you want to do that in Excel, they also have a Bessel function you could use. So we could go after that approach and do so. But I thought I would also, because it's probably more relevant to what you would do on a test, I thought it would be more useful to go through here and show you how to do it on the chart right here. So again, here's our triangular fin. And here you can see that we have LC is proportional to L, so LC now is going to be L, which is going to be 0.04 meters. Since T is 1 millimeter, we can calculate AP is going to be LT over 2, which will be then 0.04 meters times 0.001 meters, all divided by 2. And the answer for that, for AP, is 2 times 10 to the minus 5 square meters. So then this combination of LC to the 3 halves, square root of H over K A sub P. When you plug in all the numbers, what you get is 1.41. And we can show here that if you pick a value close to 1.4, we're going to put it up to the line here and then carry it over. You get something roughly around 56%. It turns out the value of 0.56 is what you get from using the Bessel functions for the direct calculation. And it looks like you're pretty close here as well. So we'll use the 0.56 as our fit efficiency. So again, going back here, so table 3.5 or the charts, what you get is eta sub f is about 0.56. Now, we also need the fin area. So let's go back. Oops, wrong one. Let's go back here. We'll go back to that chart again, or the table 3.5 rather. And here we see that we're provided with an equation for the area. So 2 times the width W, which is the depth in terms of our problem statement, it's 2 centimeters. We have the new length, and then we have the base thickness as well. So using that, we can get our area. So table 3.5 also provides the value of the area. And that area is, again, going to be 0.0016 square meters using the equation from the table. Alright, so we have an updated A sub f, we have an updated eta sub f. Now if you look at this problem with the new fin array geometry compared to the original, I hope you can see that the base area A sub b is unchanged because the gaps between the fins don't change because the fin base thickness is the same for both heat sinks. So that's unchanged. So we then can calculate A sub t is A sub b plus n A sub f, and we get that as a total area of 0.0194 square meters. If you recall in class, the value that we had for A sub t for the rectangular array was about 0.01 square meters, so this is about twice as much. So 2 times higher. So we're in pretty good shape there. Now going back here again, you can see that there's no reason to believe that assuming the base heat sink or the thickness of the base of the heat sink is the same and the contact resistance is the same, there's no reason to believe that our conduction and our contact are any different. So again, looking at the resistor here, RTC is the same for both situations, our conduction is the same. The only thing that's changing is RTO. So let's go back then to here and to calculate RTO. Alright, so RTO is 1 over H A sub T eta sub O. Well, we need to get an updated eta sub O. So 1 minus n A sub F over A sub T, 1 minus eta sub F. We now have all the parameters we need. We know A sub F, we know A sub T, and we know eta sub F. Our updated eta sub O is about 0.57. So again, just like I said in class, eta sub O should be very close to eta sub F, maybe a little bit larger. And that's the case here. So you plug in the numbers then to RTO. What you get then is RTO of 0.365. This then leads you to an R total of 0.621. So if you want to compare this value of R total to what we had in the earlier problem, we had an RTO of 0.463. So our total, I'm sorry, I'm looking at our TO right here. Our total in the previous one was 0.720, so it's gone down. It went from 0.720 down to 0.621. So it reduced, which means the heatsink is doing a better job of removing the heat. And the final thing we need to do is calculate T chip, which will be T infinity plus Q times R total. And what we get for this case here is 51 degrees C. Looking back here, we got 56 degrees C, so we're doing a little bit better here. So the answer, going back to the very beginning, is would using this alternative heatsink result in a lower chip temperature? The answer is yes. Yes, it does.